Welcome once again. We're going to continue our discussion in Chem 336, and we're beginning a brand new topic, and that'll be nucleophilic substitutions. Just as the name implies, we have not really talked much about nucleophile, but we've used a different name in Chem 175 or even in Chem 330. That's a base, okay? Anything that's basic, a base, like an acid, we have a base. Base can act as a nucleophile. We'll talk more about that. But what it's really happening is you're substituting one with another. That's essentially what we're going to be doing. So I have created a little graphic just to demonstrate what it is that we're learning. So I'm going to call my reactant as a substrate, and a substrate contains a group that's ready to leave and be substituted. We're going to call that a leaving group. The leaving group is attached to a carbon in the substrate. And then a nucleophile, which is considered the attacking agent, attacks the carbon containing the leaving group. And then in the process, the leaving group comes out and the nucleophile takes the exact same position of where the leaving group was. And in the process, the nucleophile is now in place of where the leaving group was. Okay, now there are two different types of substitutions we would learn, as you will see in the upcoming videos. But this is essentially what we're doing. We're substituting one for the other. Now, what is a nucleophile? Well, as I said, we haven't really looked into it in Chem 330, so this is a good place to just get it out of the way. A substance that's rich in electrons, basically any substance that's really rich in electrons, can be called a nucleophile. So nucleophile themselves can exist in two different native forms. It can be either negatively charged or it can be neutral with lone pair of electrons, like in NH3. If you remember going back to your 170 and draw those decrypted structures, you'll see NH3, which is ammonia, has a lone pair of electrons. Water has two lone pairs of electrons. You know, phosphine, pH3, has a lone pair of electrons. All of these elements are neutral, but they have an abundant supply of electrons. And these can generally donate their electrons to some other element. That's why they're called a nucleophile. When they donate, they end up attacking the carbon containing whatever group that it's donating the electrons to. So nucleophile can be either negatively charged or it can contain a lone pair of electrons. In that case, it will be neutral. Okay. Typically, bases are called nucleophiles in organic chemistry. Okay. Nucleophiles can be strong or weak. As with anything like ups and downs, good and bad, nucleophile can be really strong or weak or somewhere in between, called moderate, but we're going to focus on the two extremes because that makes life easier. What essential prior knowledge do I need to know from Chem 330 just to handle this substitution topic is very simple. You need to know how to identify a carbon in a substrate, okay, that contains the leaving group as methyl or primary or secondary or tertiary. Now, let me quickly summarize it. A carbon with 3 hydrogen is methyl, right? Carbon with 2 hydrogens is primary. Carbon with 1 hydrogen is secondary. And carbon with 0 hydrogen, well, basically what that means is your other 3 bonds are all different, and that's tertiary. Okay, this is the basic knowledge you have, and then we have a few more things that we will look at it. So again, this is an introductory video, so I don't want to get into too much details. Types of substitution reactions. We're going to learn two types of reaction, SN2 and SN1. SN stands for substitution nucleophilic. Don't worry, I'm not going to quiz you what SN stands for. 1 stands for unimolecular, 2 stands for bimolecular. We'll come back to all of this in detail, okay? Now, I have listed a list of common bases. I've listed some negatively charged bases, and then I did not categorize them, and then I have a few that are in blue, or I think purple. These are strong bases, okay? And then the ones in the red are bulky strong bases. Now, if you notice, the ones in the purple or even the red, within their color category, in this case, I have the negative Na here, okay? And here it's missing the Na. Why do I have that? Is because I'm teaching the class, and you can get used to my learning style, but if you plan to sit for any professional exams, they may have it as CH3O minus or CH3O minus Na or CH3O minus K. Both of these mean the same. It's just sometimes they have the sodium, sometimes they have it without the sodium. So these are the strong bases. These are the bulky strong bases. And these are also some of the negatively charged bases. And we have some neutral bases, as I've already shown. Don't try to get in too much and think hard about these. It will become natural, and you do not have to necessarily memorize these, okay? And then all reactions have to be carried out in some kind of solvent. Primary for this course, we're going to classify it as protic solvents and aprotic solvents. Protic solvents are solvents that typically can mix with water or have polarity to it. Aprotic solvents are solvents that typically don't have no polarity to them. They are nonpolar is what it really means. So protic is polar, aprotic is nonpolar. And I have a list of leaving groups. For now, I might give this to you on all the worksheets so that you can get used to it. What this means is this has the highest tendency of leaving very rapidly. So rapid tendency to leave, very slow tendency to leave. Basically, we talked about a leaving group, right? This is generally the tendency. If this is the leaving group, it has the highest possibility to be replaced. Whereas if you have this as your leaving group, it really doesn't want to leave. Okay, again, none of this have to be memorized. So we're learning about we're going to put all of these together: the nucleophile, the substrate, the leaving group, and the solvent. So there's 4 components to it, and we're going to try to address those using the 2 substitution reactions, SN2 and SN1. SN stands for substitution nucleophilic, 1 stands for unimolecular, 2 stands for bimolecular. Like I said, I will explain more detail what those 1 and 2 stands for as we get going, okay? Try not to think too much and try to memorize everything on the screen. Just take it for what it is now and try to understand the concept holistically, and then you can actually learn in more depth, and then you would not find the need to memorize any of this. All right, so stay tuned for SN2 and SN1.